In this video, I'm going to show you how you can run a one-way ANOVA. ANOVAs are used when you want to compare the means of more than two groups. So in this data set here, I have people whose weight loss was recorded from taking a diet. In fact, there were three diets, diets 1, 2 and 3. Their weight was taken before the diet, after the diet, and then the weight loss is here recorded in this column. So the two columns of data that we need are this column with our data, and then this column here with our codes. Because we have a third group here, this diet 3, this is why a t-test is just not any good anymore. So we go to Analyze, and you can perform a one-way ANOVA using the compare means and the one-way ANOVA option, but there are some limitations in doing so. The first things you need to do is you need to test assumptions of the one-way ANOVA. You need to test that the residuals follow a normal distribution, and you need to check that you've got equal homogeneity of variances. So in order to have those options, it's better to go to General Linear Model. We have here our dependent variable. So this is weight loss. That goes here. That's what we're measuring. It's scale. And then we are interested in the diet group. This goes here into fixed factors. Now there are lots of different options here. Some of them are relevant, some of them are not relevant. Model, for example, you leave this as it is. This could become useful if you're doing a two-way ANOVA, but we're leaving that one for now. We don't really need to go on to contrasts. Plots, again, you can if you would like to visualize your data. So this again is more useful when you've got your two-way ANOVA. Your post hoc tests, now these are quite important because if you get a significant difference in your one-way ANOVA, and the null hypothesis for your one-way ANOVA is that all the means are equal, you need to know which means are different from each other. So if we go here to post hoc tests, we can move over the diet factor, so in this case it was our grouping variable, and we can select Tukey. Now there are lots of different types of post hoc tests. Tukey is one of the most robust, especially if your data are not quite perfect. You may have a preference for using a different one. Also, if you do find that you don't have equal variance, then there are some other options down here, but for now I'm going to tick this. I'm going to press continue. Now I want to know whether or not the residuals of my data follow a normal distribution or not. So I'm just going to click this and it will generate a new column of data here with all my residuals, and this will allow me to then perform a normality test. Press OK, options. So I'm going to tick here for homogeneity tests because this is how I know if I have equal variance. I'm also going to tick for descriptive statistics, and it might be for your work that you need to do an estimate of effect size. I'm not going to tick that here, but if you're looking for this particular option, that's where you would find it. And then continue, and we don't need the bootstrap option for now. So I'm going to press OK. So our output window appears. It gives us a bit of a summary of our data. So what I can see here is that we've got over 25 samples in each of our groups, and our group sizes aren't too dissimilar from each other. So down here we have our Levene's test for equality of variances. Now this tells us whether or not our data do have equal variance. So how much they vary within each group. Is that the same amount of variation in each group? And in this case it is, because our null hypothesis is that everything has equal variance until we can prove otherwise with a significant p-value. We haven't done that here, so we can say yes, everything does look equal at the moment. This table up here that I missed out, this actually tells us our mean weight loss. So if we do see a difference later on, it might be worth noting that diet 1 had 3.3 kilograms, 2 was about 3 kilograms, and 3 was actually about 5.1 kilograms. So that could be interesting to note later. But before we move on and look at the rest of the tables, we need to make sure that our data follow a normal distribution. Now, most people would say that somewhere between 25 and 30 samples in each group means that you don't strictly have to adhere, you don't have to have a normal distribution. You can get away with it because the ANOVA is quite robust. But we're going to just check anyway, because this might be something that your lecturers would like you to test and to know about. So we're going to test the residuals. So in previous videos, I explained that it's important to test the different groups. So you would normally have tested diet 1 and 2 separately, for example, for a normal distribution. In this case, with an ANOVA, you could do it that way, but the actual assumption is about the residuals. So that's why I'm using residuals here. And then I'm going to go back to analyze. So this is one way that you can find your normality test, so your Kolmogorov-Smirnov test that I would have shown you in previous videos. So I'm actually going here to legacy dialogues instead of using one of these options. But if you prefer these options, then that is completely fine too. One sample, KS. So it's KS, and that should be ticked here for normal. And then we just find our residual column that's just been created here, and we move this over and we tick OK. This now gives us our table. So this is our test statistic, 0.038. So if you wanted to note this down, you can. And here is our p-value, which is actually pretty high, and therefore it is not significantly different from that of a normal distribution. So we can scroll back up now to look at our test. So here is our one-way ANOVA. There's a lot of information in this table, but I want you to focus in on this line here that says diet. This is the thing, this is our variable, this is what we are testing, this is what we're looking at. So what this is telling us is that this is our test statistic, so you may want to quote that. This is the degree of freedom when we're talking about diet for 2, but then we follow that with this degree of freedom. So it depends on your subject on how you might want to write this. This is our p-value here. And as you can see, it's very significant. But all this is telling us at the moment is that there is a significant difference between the means. So that's all we know at the moment. We don't know which of those diets, and we remember this is the weight loss here, we don't know which ones are different from each other. So for that information, we have to go to our post hoc Tukey test. You might remember that I ticked that box earlier. Now, some statisticians will say that if this test is not significant, you shouldn't bother looking at this, you should ignore it. Whereas others say that there are circumstances in which you might not get a significant difference here, but you can here. So again, this might be something that you have to double check with your lecturer. But all being well, you will get a significant difference here that allows you then to look at this table, and then it compares diet 1 to 2 to 3, so it does a comparison between each of them, a little bit like doing several independent t-tests. But the more times you perform an independent t-test on the same data set, the more chances you have of generating errors and getting a false positive result. The Tukey, in a nutshell, is using a correction for that. So although it is essentially rerunning these tests in multiple comparisons, it's making a correction for the fact that you are rerunning. So this is why it's much better to do an ANOVA than it is to just take your diet weight losses and to just do lots of independent t-tests yourself. So this is our significance column, and you'll see that we'll have 1 and 3 will be repeated here and here as well. So you will get a few that are repeated. What we can see here is that actually diet 3 is significantly different from both diet 1 and diet 2, but that diet 1 and diet 2 are not significantly different from each other. So in a nutshell, that's how you perform a one-way ANOVA.